Well, hello. We are Ryan Warnes and Carlos Garcia Prado talking to you from Singapore. Oh, wait, no, we are at home. But anyway, this is Hacking the Box, and we're going to talk to you about fiddling with decompilers. So very briefly, the agenda, we're going to talk about, how to do source code analysis without the source code. Then we're going to see how, decompilers are hard. Afterwards, we're going to see that IDA is hard as well. We are going to introduce our solution to this problem, namely a library for interacting with the hex-race decompiler, making your life hopefully easier, called FIDL. And at the end, we're going to see how you would be able to do this at the scale. We'll be reversing and decompiling at scale. So yeah, who is this? Ryan?
Yeah, my name is Ryan Warnes. I've run the gambit in terms of sort of low-level reverse engineering stuff. So I've done, malware analysis, vulnerability research, worked on Windows, worked on Android. I've kind of, done just about everything. So.
And I am Carlos Garcia Prado, also go by Carl OS. It's pretty easy to distinguish us because I'm the one with the accent. I actually did not study computer science. The computer science guy is Ryan. Did physics a long time ago in another life. I really like IDA, Python, and Windows stuff in general. Love to automate stuff, and that's why we are here. And I've been like around 10 years in offensive security roles, different ones. Before we start, we would like to give a shout out to some other people doing like what we think is very interesting work in the compilation topics. And yeah, definitely Patois, or I don't really know how to pronounce that name. Everything from this guy, it's totally worth it. It has like extremely good IDA Python plugins, so go check it out. And of course, this tool is very useful as well. We use it all the time.
So yeah, kind of to set the stage for what we're talking about and where we think FIDL slots into the binary analysis, reverse engineering, VR process. Usually what ends up happening when you're going through and doing something like VR is you'll have your fuzzer running in the background, hammering away to try to do code coverage and all those kind of like dynamic instrumentation metrics. And then independently of that, you want to be looking at the code base sort of yourself, right? Because that lets you do things like, maybe I want to drill down in a particular area, or maybe I have some sort of data definition wrong in kind of my fuzz case, and it helps you sort of independently in parallel build out these different like use cases and places you want to look and things you want to do. So when we're talking about source code analysis, it's both looking for bugs, but also it gives us a lot of insight because we have things like what functions call what functions and sort of some code flow structures there. We also have this idea of we know the data structures, we know which structures are meant to work in tangent together. If there's any things like structures and structures or reference counting or any kind of things that would be prone to those logic errors, basically by looking at our source code, we can sort of understand the code base as a whole. And that's more or less a different mechanic that we can both use to find bugs while we're fuzzing, and then also take that information and feed it back into our fuzzing framework with sort of some, increased granularity. So we're writing more accurate fuzz cases, and we're ensuring that we're touching more pieces of the code that way. And this holds true for whether you're doing VR or just kind of general purpose reverse engineering too. So when we talk about the problem that we're trying to solve here, when you're doing some kind of VR project on something that's closed source and you don't have the source code to rely on, your workflow is ideally more or less the same. You have your fuzzer running on one side, you're sitting there crawling through the binary. Oh, I found something interesting. Is that a bug, or can I use that to inform my fuzzer on the back end? But the problem is when we don't have source, it probably makes sense to most people, but we also lose all of the information that we would normally be looking for when we're doing our manual analysis process. So a lot of that things like code flow might be harder to track and harder to understand, or even we have these sort of sophisticated disassemblers nowadays, but there's no guarantee that whatever heuristics they're using to massage and manipulate the binary will accurately represent things like how big are structures, which structures are meant to interact together, or what kind of data types do structure members have. So all that information basically gets lost to us. And when you're talking about code flow and you're talking about vulnerability research in particular, C++ is the classical example where, because you have a bunch of objects in memory all passing different structures around and calling function pointers in and out of each other, tracking all of the code paths that a binary can possibly take gets really complicated really fast. And by nature of how disassemblers work, you lose things like cross references usually for B table functions and some of that kind of information that's super useful to us when we're trying to understand how a binary works and how to, by extension, fuzz it and attack it for vulnerabilities. So fundamentally, we lose all this information that we would be relying on because compilation is a lossy process. And really what I mean by that is that when a developer builds source code or pushes it through a compiler or some kind of build framework, the compiler is only beholden to make sure that the thing that runs in the final binary is what we intended to write as an author. But it's not beholden to the how it gets from point A to point B. So things like structure definitions could be moved around. There are optimizations in place that might change how code works or how functions are compiled or how it looks or how it runs. Then on top of that, another way to think of it is when you compile, you have basically everything you would have if we were looking at it from like a source code perspective. So things like header files, type defs, function definitions, structure definitions. The compiler has all of that information and then basically throws away the stuff that's unnecessary for execution. So the compiler doesn't have any need to know how structure A is defined as long as it knows where the data is supposed to go sort of in relation to everything else that's using that structure. So what ends up happening is we have all this information in our source code, but the compiler only needs like 60% of it. And that's before we even start to talk about things like function names, local variable types, all the stuff that would normally be in like a PDB file, for example. We lose all of that. So when we're trying to keep our workflow the same for doing vulnerability research or some kind of binary analysis, it would be super helpful if we had some tools to essentially wrangle that compiled binary and recover or take a best guess at recovering some of that information that gets lost in the compilation process. So that's really what we're talking about here, and that's really where you'll see our tool comes into play, because normally what will happen is we have tools already written for us called decompilers, which do some of this for us, but we'll see where that kind of breaks down and where it becomes kind of complicated for us to use out of the box. So just to give you a general idea, when we're talking about a decompiler, we just kind of walked you through the base case where I said the compiler has all the information when it's building a program and it throws some of it away. But you can rely on things, if you want to reverse that process, you can rely on things like common patterns that are seen in compiled code or sort of behavioral things that you would expect, and you can kind of run this heuristic over it to build a more or less accurate representation of how these things work. So just as kind of a quick and dirty example, when you're going through and these decompilers are trying to lift up all this logic out of a compiled binary, you'll have your assembly code sort of at the base layer, and they'll all have disassemblers and they'll understand how to interpret these instructions. From there, you can track things like, is this a stack variable or an allocated buffer or some other kind of data structure? And you can convert these simple, one-line instructions into kind of a higher level representation. So, in this example, EBX is some kind of maybe function pointer or structure pointer rather, and we can convert sort of raw assembly into kind of a more logical representation. And then from here, there's not really a silver bullet or a quick answer. It's basically the dragons of optimization. But what it does is once we have this higher level representation of what all this code is doing, from there, those are the building blocks that we can use to really start to make some guesses and assumptions and deductions about what a function is supposed to do. So once we have that sort of IL, or that intermediate level representation, we can take that and build that into what's shown here, which is an abstract syntax tree, where essentially you've mapped from sort of raw assembly to some kind of thing that more or less looks like a logic tree. And that logic tree lets us start to tease out things like conditional statements or switch statements or loops or any of that kind of stuff that you would see in your source code. So as the result of all of this, once we've done our sort of fancy optimization, we get something that looks similar to source code. There's no guarantee that it's exactly what we would have expected when there's no guarantee it's exactly what we wrote when we were compiling the code, but it's a pretty close approximation. And this is all kind of a simple example, but obviously as things get more complicated, as you have more functions, as you have more structures, as you have more cross references, this all blows up kind of exponentially. But that's kind of the idea for decompilers, is we want to step by step, piecewise convert from a higher level, from a lower level representation to something that looks like source code, and we can work with that because it's a lot easier for us to process the box on the left and a bunch of boxes shown on the right. And then the AST, if you've ever looked at IDA's existing API, this is sort of their core mechanic. This is their favorite thing that they like to use. This is what their API is built on, is kind of iterating over this AST in order to make some kind of scripting framework around it. So in general, there is a lot of work shown on the decompiler. It's not a sort of new field of study. There's lots of work. There's lots of different decompilers out there nowadays. So if you want to dig into it and get a little more detail about what some of those dragons I talked about on the last slide look like, here's just a simple LLVM doc. You can go ahead and dig into that at your heart's content. But for us, for this talk, luckily what we're going to be able to rely on is that a lot of this fancy work, a lot of this magic, a lot of this computer science is already done for us with tools like IDA on the left or Ghidra on the right, where they've already kind of gone through that process of taking assembly code, lifting it into a higher level representation, and then they produce the end result, which is shown on the screen here, which looks a lot like C code, maybe not very pretty C code, but pretty enough for us to kind of process and understand. And for now, it's enough to say that there is an AST that's kind of backing what's shown on the screen here. So if I want to script against this output, I'm not scripting against like text or something like that. I'm scripting against whatever the decompiler's representation of a function is. And where it really starts to break down from a binary analysis process, which Carlos is going to go into in a couple seconds, is while things like Ghidra and IDA are very sophisticated and they've done a lot of work in sort of that language lifting component of it, by nature of being very complicated, they have kind of a very complicated API. So when we're trying to do things like write scripts against it to do binary processing, there's a pretty steep learning curve. And in a lot of situations, it's really hard to massage the existing default API into doing what we need it to do from a binary analysis perspective.
So yeah, the reason actually behind the bad joke saying like ain't nobody got time for tap is that the decompiler in IDA, let's talk just about IDA and focus on that. It's very good. It's very mature, but it has been designed apparently to be used like kind of interactively. You're in front of your function, you're doing your analysis, you press tab, and then you switch to decompile code. And and life is better, but still you're just looking at one single function, then you move to another one and you do the same. So we would like to have something that actually is more programmatically and that we can tackle like many different functions inside the binary, like inside a script or a program, not necessarily having to be in front of it. So yeah, there was many shortcomings for the way that we work reversing binaries. So that's why we brought here our own solution that it's called FIDL. You have it in there in github.com if you want to go for it. I will show you links later. And we kind of define this thing as the same API for IDA Pro's decompiler because the raw API, it was like too complicated for us. It was, I had like a very, very steep learning curve. So just let me mention that when we put this thing out there, I tweeted, whoa, finally we have something that makes the IDA Decompiler API usable. As you may have noticed, I'm not exactly an English native speaker, so there was like let's say, a poor choice of words. So we got this answer from Ilfak. In case somebody has been living under a rock, Ilfak is the creator of IDA Pro. So yeah, there were some people like piling on and saying like this is very inflammatory. But at the end of the day, Ilfak said, "Oh wow, I like this. This is wonderful." So we gained his love again. So everything is cool. This is, so to speak, Ilfak approved. So yeah, but let's talk a little bit about the internals of FIDL. So one thing that you're going to be using all the time if you choose to use FIDL is this thing called control flowinator. We know it's a dumb name. We like dumb names. This essentially is kind of a data structure representing a single function. And you can think about it, it's like a mix between a control flow graph and this decompilation output that we showed you before. And in order to understand this thing better, imagine that you have like a control flow graph, like the one you have in assembly mode. But now every node is actually a high-level code artifact. It's, for example, like an if statement or an assignment, or, it's like a function call or whatever. So it looks, when you are debugging it and look at it as something similar to this. So essentially, if you have been using IDA, you are used to this representation that is a control flow graph with just a very, you're deep into the binary, you're just looking at the assembly instructions, or if you're lucky enough or to have the decompiler plugin, then you are used to this. This is exactly the decompile code of this assembly on the left. So now what you have with FIDL is something in between those. So there's this control flowinator that we show you, in which you see you have like kind of the best of both worlds. So you still can work with a graph. So if you see, it's like logically very similar to the one that you had at the left. So you can use all those very juicy algorithms. You can traverse the graph and look for all the paths in between A and B and all those things that are like very natural in order to analyze a binary or looking for something. So it's something like in between those two that you already know. And as an example, look at this node, something that we said before. This is an assignment. That would be, this node would represent actually this line of code. Right now, at the very beginning, it's just like a simple node in a graph, but there is many APIs. FIDL is pretty rich in order to, let's say you want to zoom into this node and then take a look at the details. For example, is the left-hand side, like is there a variable in there? Is the right-hand side a number or whatever it is? So you can do all that. But at the very beginning, with the control flowinator that I repeat, you're going to be using all the time if you script with FIDL, the first thing that you get is kind of a high-level overview of what is going on in this function logic. So yeah, here we just wanted to show you that this really scales. So even if you have a function like this one in the left, one of those functions that you're reversing are like, oh no, I don't wanna mess with that. And the thing that you see in the middle would be like the control flowinator associated to that one, and on the right, we're just showing you, like it's zooming in there so that you have an idea of how complex this thing is. So this thing it scales like very, very well. And by the way, we're showing you those graphs all the time. And you can generate those things because those are produced by FIDL itself. when you're debugging. So if you're really deep into FIDL, if you want to contribute, if you want to look at the algorithms and improve them and send us a PR, we would be like very happy. Nothing to complain in there. You have those, let's say, those facilities in order to do some debugging as well. So this is just like a dot generated graph. And yeah, talking about dot, like again, we wanna make clear that this thing is ready for like real life binaries. It's gonna take more or less time, of course. But even if you have a function like this, that is, like it's reverse engineer hell, you can create a control flow initer. This is just, just created a control flow initer of this function. And you see in here, I did not display that, but if you see in here, okay, just IDA says like no problem at all. I just created the control flow initer object that must be huge. If I try to display it, dot is gonna crash, at least on my machine, saying that is, out of memory. So once again, what we're trying to say in here is this thing is ready for real life binaries. We have been throwing like everything at it, and it works pretty well. And another thing is like we have tried to make this thing kind of batteries included, so kind of the same philosophy behind Python. And when you create a control flow initer for a specific function, by default, it's going to have a lot of very interesting information. For example, it's going to have information about all the function calls inside this function, of course, the local variables, the arguments, and return types, many things that are accessible to you like very easily. And this is just a code snippet showing you, this is something that you're going to be like doing like all the time. Of course, you're going to be importing FIDL. Then you create a control flow initer that has a couple of parameters. One of them is just one address inside the function that you want to represent or get information from, and the other one, most of the time, you're going to be it's going to be good that you set it to false, because then you're going to get all those goodies. And as I said, you have this object C that is just like the control flow initer, and very quickly you can access them very, let's say, comfortably. You can access all this information that you would suppose it should be easy, to get that, those basics about, I want to know about, in this, as you see in this snippet, I want to know about this specific function. Tell me about all the local variables. Tell me the names, the types. Are they an array or not? Are they like a pointer to some other complex type? All this is encapsulated by FIDL, so you don't have to put a lot of work or almost any work in getting the easiest things. This was one of the design principles. We will try to give you as many things already digested for you, so that you can concentrate on the things that matter, not just being lost in the details. So
yeah, so like Carlos was saying, we've kind of gone through how FIDL's built in the back end, and we'll now show some examples of what it can do. But basically, there's kind of like a so what question. Why do we bother? Why do we do this? Why is this helpful? And for us, like I said, it's not that existing tools are insufficient. It's more like the questions that I need to ask if I want to run sort of a binary analysis script, over a large section of binaries or a large collection of binaries, right? There's kind of some common things that I'd want to do over and over and over and over again. So, we're from the Flare team. We do a lot of malware analysis, for example. There are certain code patterns that you see in malware, ad nauseum. So it'd be super helpful if we had something to sort of just kind of script against those. And the problem is, because Carlos was saying, essentially a lot of IDA's APIs are meant to kind of work from a workflow where you're in front of a terminal and interacting with a binary, clicking through functions and kind of looking at functions one at a time. We had to spend a lot of time sort of digging down and really understanding what makes it tick when you rename a variable or when you decompile a function or something like that. So a lot of those APIs. It's not that they were inaccessible or anything like that, but sort of the workflow that you need to go through to make modifications and extract data in a way that's very useful is kind of tricky. And if you're not using the AST, it gets even harder because, like I said, a lot of sort of, at least from our perspective, what we found in practice is that a lot of the way the APIs work is they're designed around that AST, and using that as kind of your core data source, which is sort of something not that we wanted to avoid, but for flexibility reasons, we had to dig a little deeper, which meant a lot of DIRs, is this function right? And this one kind of looks like it, but then you have to call function A, then function B. So we did sort of all that information for you, because the idea is like, we want to give you a framework to allow you to focus on sort of the big picture stuff. Like if I just want to say, I want to scan a binary and look for these 5 things, I don't really want to have to worry about reprocessing the AST every time or re-understanding some sort of mechanic or edge case or something like that you ran into once about an assignment statement or something like that. So we've extracted all of that away, and the result of that is if we have these sort of use cases like this. So as a very simple example, one of the most common things you're going to do, particularly when you're talking about malware analysis, is I want to find all the references to a function and then extract a parameter from it, right? So what we have shown here is, the set dialog item text function call, but, it would also be analogous to if you had a get proc address call, like understanding whatever that string value is in order to extract whatever kind of dynamic function lookup was being done. So if I want to take this example and say I want to find instances of a function call inside of a function, so I want to find references to my set dialog item text A, then I want to grab any argument that is a string, and I want to get that string and print it out, or in some cases you could use it. You could imagine if it's a debug message, you'd be able to log that or put it in a comment or even rename a function sort of around that functionality. So this sort of simple extraction of parameter data is super useful. But not where it breaks down, but where it sort of hits the road for us is if I want to do this with IDA's existing API, everything will work fine, but I need to write sort of a class like I have here, which, if you're unfamiliar with IDA's API, essentially this visit expression function that I have defined on line 13 is there to function basically as a callback. So you would say, hey, look at a function, IDA will decompile it, and then IDA has access to its AST, so it'll iterate through the AST for you more or less, and then you'll get this callback as it visits certain nodes or certain expressions depending on how you build your class. And so this is sort of the intended solution when you're talking about IDA's API, because you would basically iterate through the AST, you would look for function calls, which I have shown on line 14, and then once you have an instance of a function call, you can dig down into it. So is the function name set dialog item text A? And then from there, you can go through the parameters. For each parameter, you can check to see if it's a string, and then if it's a string, you can extract it, right? And this is all, it's all well and good, it all works. And once you're familiar with sort of the workflow of it, it's fine. But where it breaks down for us from like a general perspective is it's kind of twofold. One, on line 16, you can see an instance of us taking a node, which is in the I variable for this case. And this concept of I.x and I.y are how you iterate down the tree. And when we're talking about the AST, again, remember, we're saying IDA visits it for you, but there's some instances where if I'm doing a heuristic, like a function call or an assignment or something, I need to be able to walk up and down the tree sort of in a way that makes sense, right? And if you're trying to take that workflow and make it a generic sort of sequence of steps you would do over and over for different functions or different parameters or whatever, then adding on top of it, being able to walk up and down the tree, the more steps you have to take to get the information you want, it kind of blooms out of control. Because like in the case I have shown on this previous slide here, there's nothing like a return value, and the decompilation is also very clean, right? So there's no references, there's no casts, there's kind of nothing around my set dialog item text a function that would make this an unusual case. But the more complicated your logic is, or if you're in an if statement or an assignment or anything like that, then as you walk up and down the tree, sort of the use cases kind of expand exponentially. And then the other piece of it is, this is more or less hard coded to set dialog item text A and looking for a string argument. But if I want to change it to a different function name and say extract a number, then I have to rewrite all of this code essentially. I can copy and paste it, and it's only a couple line changes, but basically there's sort of a twofold problem of one, it's hard to convert this visitor prototype into something generic that you can use over and over when you're doing your analysis work. And two, you can even just see from the amount of times that I'm accessing I.X or I.A, and then there's an index. There's a bunch of kind of internal mechanics about IDA's underlying objects and representations that it's not that it's hard, it's just that it's a spin up process and it takes a lot to kind of get your head around the first time. So what we've done is we've done all that work for you, and when you do this in FIDL, you get something like this. So we build a control flowinator for the same function. We have already gone through and sort of done everything that I've shown you in this visitor class on the right, and we've converted all of that into members in our control flowinator object. So I can extract all of the function calls with our c.calls mechanism. And then for each function call, I can just go through and just check the name. And these are all sort of names and parameters that all make sense, or they all are easier to read is the sort of end goal for us, right? And the idea being like, function called .name is a lot easier to extract than like calling a name API on a 3 reference deep sort of data member. So this is just a quick example, and Carlos is going to go into some more now about, we've sort of done the tedious mechanical parts for you, and we've integrated that all into our control flowinator function. So now when I want to write sort of a dynamic processing script, it's a lot easier to write code that's shown on the left than the code that's shown on the right, right? And then you have access to, like I said, a bunch of named tuples. We'll go through some more examples, and we have a bunch of essentially generic functionality. So, anything that you would think of as like a semi-common problem you run into when scripting against a binary is something that we've already sort of wrangled the decompiler to expose to you in sort of an easy to use and easy to script against way.
So yeah, as Brian just said, one of the things that was important for us, it was of course like that this is easy to use, because if it's not easier to use than the raw API, then kind of defeats the purpose. So we try to, if you see the number of functions inside this, let's say, little API that we built on top of the raw API, there are like many functions. Some of them are like rather more or less, let's say, complex, but some of them are actually like a couple of line wrappers. But still, the idea is that if you see this wrapper in your code, it's going to have like a clear name. It's going to be wrapping something that you could do it, but then your code is going to be larger. It's going to be less clear, and it's going to be terribly tedious to do that all the time. So we try to. There's going to be like bazillions of functions in there. We're not going to go no way through those. They're pretty well documented. Let's say we put some work on that as well. So every time that we make a minor change or a large one, and we push the code, so documentation gets automatically generated from the code. And it gets pushed to read the docs. You're gonna get the links afterwards. So if you go to read the docs and search for any API, they have like kind of logical names, we think, and so everything's gonna be there, and that you always have the latest. So it's gonna be updated. This is what we're trying to say. So yeah. But we're going to show a couple of more or less concrete examples to give an idea of the things that you can do. They're not the most complex ones. You can really go down the rabbit hole in here. We try to strike a balance in between. Okay, look, this is rather powerful and easy, and so let's go for it. This is kind of a bit contrived. In this case, this C2 that you see in there is, of course, like a control flow inator objects. You're iterating through all the nodes in this graph. Remember that the thing at the end of the day is a graph. And then we have, for example, this API find elements of type. And what you have to do is imagine that you want to search for, I want an element, I want a node. I want to find a node that it has like a number inside it, or it has whatever, like a reference or a pointer or whatever. And so you can do very easily this thing like in a loop. You say, okay, let's go through all the nodes inside this control flowinator. I want to find elements of this type, and the rest is just like a format, like a complicated format string. In this case, we're looking for numbers. And you see here the output, you have all those addresses and the number that is found in this, inside this node. So if you click whatever address like that one that's 67, it's going to take you to the line of decompile code. And then you see indeed there is like an occurrence of a literal, so like a number. And this is, in this case, this 67. This is, as I said, like a very contrived example, only to kind of show you most of the things, most of the tedious things, most of the things that you're going to be using all the time. Like, I would like to search all the numbers that there is in this function. It's already in there for you. Clear APIs like find elements of type, this and that. And in this specific example, this is probably like an offset into a structure, so it's not very interesting. As I said, very contrived, but let's use exactly the same logic in a real case. So this is from one of our colleagues. It's a snippet, of course, from something that one of our colleagues uses in the wild. He was working in some malware that, of course, malware being as sneaky as it is, what it was doing is it had all the strings inside the binary encrypted. All those strings were decrypted in real time. This is this first line that you see in this strings variable. It's not really important how. This is just a specifics of this very specific malware. Just keep in mind that this strings is just an array to many strings that this malware is using, that when you're sitting on your disk is just garbage. Right now, we kind of emulated that the malware is running and decrypted all this stuff while it's running. And we have like an array of strings. This is another very, very useful API that you're going to be using all the time. So in this case, our colleague just realized that the malware is always using or referencing this array of strings that is now in memory decrypted. So what we're going to do is like search for all the calls inside the binary to this specific function. And then we're going to see, okay, for all those calls that you see, just give me the first argument. We're just checking that the first argument is indeed a number, this kind of a sanity check. And then we're saying, okay, now give me the real value of this number, in this case, like whatever, 3, 4, 7. And this is being used as an index into this array. So this looks like very easy because it is very easy when you do it with FIDL. If you try to do the same thing, and again, we try to strike a balance. This is not like a terribly complicated example, but it's something like from real life, and that this thing happens like all the time in malware. So it is, almost 3-4 lines. The rest is just prints, or in this case, it's creating a comment, but it doesn't matter. It's like format string. If I throw you this snippet and you don't know anything about FIDL, you could have like a pretty educated guess like what is going on. That's we kind of strive that is something that it makes sense and it's logical, because it happens a lot that you write as whatever script and you go back then like 2 months afterwards and you're sitting there like, okay, what did I do? What is this thing doing? So yeah, this is kind of a real life example of something that is not exactly trivial, but it is way, way better. Well, the thing that we're trying to say all the time in this presentation is like life is better with FIDL. We may be biased, but we think so. So yeah, there's like, of course, like APIs for everything, and as well for interacting with the GUI in case you want to do some things that, you know, printing lines or just putting colors on lines that match a specific criteria that you're looking for. So they're like many things. One of the APIs that we use all the time, I would like to tell you about it, is display all calls to. That, of course, you can imagine what it's doing. Imagine this case. It happens. This example is more from the vulnerability research part of things. Imagine that you are looking at the binary, and of course, you know, you don't have symbols, so you all have those kind of function names, sub underscore something something, and life is less good than it could be. But by reversing, you realize, oh, look, this function actually looks like it's doing some kind of logging. And in the arguments, it always, when it logs, it has the original function name of this specific function that is doing the call. And this may sound like very familiar to many of you because this happens a lot. So when you identify one of those that are doing some logging or printing error messages, you know, it says like, okay, function original name, error in this and that, error code 127. So it's kind of, let's say, leaking this information that can be very juicy, because if you're able to harvest all those things and then rename those functions, then you get a lot more visibility and a lot more context on like what is going on while you are reversing. Again, we can all agree it's much better to have function names. So yeah, exactly. This is what we did. So there was all those references to that function, but of course, if you just go there and press X, you see that, but it's not helping much. But if you just do, as you can see here, simply display all calls to and the function name, you see all this. And this is very interesting to kind of, let's see, test your assumption that this is actually very quickly, that this is actually what you think it is. And in this case, for example, we can see the third argument. It appears that is, you know, it's always like unique. So it appears that yeah, supports our thesis that this thing is leaking the original function names. So now you can, of course, like do something a bit more complex and just take this third argument, very easy with FIDL, and then you rename the function doing the call. That's very, very helpful.
Yeah, so just to kind of wrap up and put a little bow on this section, like I said, we've said it a couple times, but the big takeaway for us is that when you're confronted with sort of the problems that you normally run into that require scripting for, you know, malware analysis or VR or whatever it happens to be, again, it's not that the existing tools are detrimental or deficient or anything like that, but our goal is to essentially extract away as much as possible worrying about the mechanics of, you know, how the actual decompiler works. So theoretically, right, if you think about it, what we've shown so far in terms of examples, that could almost be independent of any decompiler that you're using, right? Like we built it on top of IDA, and we built it on top of IDA sort of for very specific reasons. But the idea is, if I want to now write a script, so like some sample things that I've done with this is things like, oh, this is find all references to a string decoding function, extract the keys from the parameters. That can all be done with FIDL, and then you can just feed that into, you know, some kind of other tool like FlareEMU or something like that to actually do the string decryption. That's a pretty common one. Or because we have this control flow editor that's built on top of kind of logical statements seen in code, you can do things like if I want to track variable assignments or taint tracking, or I know this variable is a structure, so find all the structure members that are being referenced. The idea is we've built FIDL and the control flowinator to, as much as possible, extract away the mechanics of actually walking an AST. So there might still be cases where it's easier for you to get a call with FIDL and then start walking down the AST manually to extract some piece of information. But the idea is like those cases are kind of edge cases, and in the majority of situations, you'd be able to just rely on the code that we've provided you and not have to worry about sort of well, what kind of node is it? Oh, it's an addition node, so I need to do this logic versus it's a subtraction node versus it's a call or assignment. So we've kind of gotten rid of all of that. And basically we've exposed all that as generic functionality, right? So I mean, even what we showed originally of here's your control flow indicator for a function, you can find all the function calls, locals, parameters, things like that. Even that could be used as the basis for your script too. So, for us, the way we look at it, FIDL is sort of your generic functionality or your building blocks. And once you sort of extract away all the tedious mechanics of walking the AST yourself, now you can focus on like the heuristics that you care about, whether that is something to do malware analysis or something to clean up a binary or something to track object or whatever it happens to be. The idea is we've carved off a big chunk of the work that you would normally have to do in order to wrangle the decompiler to give you the information that you want. And now rather than worrying about that or worrying about, like I said, edge cases of what different ASTs for different functions can look like, you can just focus on the stuff that you care about, whatever higher level heuristics you're trying to develop, and more or less the fun stuff, right? So that's our ideas. That's sort of the design philosophy behind FIDL and the problems we're trying to solve. For more complete examples, like Carlos said, we are striving to update this where we can and as much as possible and provide sort of useful examples to the community. But along with that, we also have API documentation. So all of the functions that Carlos said we didn't have time to go over for this presentation, they're all kind of listed here. So you can see, how much we've exposed to you by default. And like I said, the idea is hopefully you can use that as kind of your foundational building block to whatever script you happen to be working on.
Okay, cool. So we hope that right now you're thinking, okay, I like this FIDL, this is a very cool thing. I like to check it out. But yeah, and it is. We still think so. We may be biased. But still, we have been talking about working on one binary. It must be a huge binary. Maybe have like 2,500 functions. So it's much better now. And FIDL helps a lot with that. But still, we're talking about one binary. And most of the time, either we're doing like, I don't know, malware reversing, or especially if we're doing like vulnerability research and we have a very large code bases with hundreds of DLLs or thousands, we're looking at large systems. We would like to do this thing at scale, so we're going to talk briefly about how we do it. So right now, this was initially our workflow. You open IDA, you load the binary, you execute a FIDL script, you close IDA, and then you repeat. So then we realized this is kind of a limitation. This is not the way to go. No, this is not how life should look like. No, thanks, but no. So we kind of thought about it, and we wrote something that we internally named the Citadel. And this has like a web interface and drag and drop and distributed processing. It executes either headless, and it's Docker prepare. So yeah, this is progress. This is 2020. This is exactly how life, reversing life, should look like. So yeah, let me show you like very quickly a tale from the Citadel. Yes, we are Rick and Morty fans, of course. Who isn't? So essentially it looks like this. And I know after the previous introduction, yeah, it's kind of turned off. It's just another web interface and another distributed processing system. So it looks like this. Here you have your campaigns. We call it campaigns. Campaigns is essentially like a bunch of binaries that you throw in there and some analysis that you want to run on them. And yeah, essentially what you do is you go here, you go to upload campaign, then you filter some data about this campaign. You drag and drop a bazillion of files in there. It's all very web 2.0. Then you go to your analysis workflow. Then you have some predefined analysis, or you user-defined ones. You kind of drag and drop this thing to the right. You can reorder this thing and say, okay, those are the analyses that I want you to run in this specific order. And, it's all like very flashy. And well, then you create your campaign, and then you have it. For example, then it appears into your campaigns and it's ready to go. What you do now is you fire up some workers that are essentially, so in a nutshell, they're like running either headless, pulling up your files, your input files, opening it in IDA and executing those scripts, sending back and forth their results. It's all very JSON-y, and then it's essentially that. At the end, if you're lucky, this is like a very simple example, of course, you get like many results. You can go in here and see, oh, okay, this looks like interesting. This is just like a very brief, just to catch your eye. This is like a very simple example. We just calculate the complexity of those functions just for the sake of this example. But you can put there like real, more or less refined heuristics if you're looking for some kind of bugs that usually look like this. You say, when you see anything in whatever function, in whatever binary that looks like this, please tell me, because what I want to do is you go here, you click in there, you download the IDB, and all the information that is displayed in here is marked inside the IDB. So you can use Control M, and you have a list of them. You just go directly to the point in the disassembly where there may be something that is sketchy that you would like to take a look as a human right now, with a human brain. Yeah, and essentially that's it. And this is where we were promising you all the time, we're gonna get it. Those are the links. You're gonna get the presentation. It's essentially just going to github.com, FireEye. This is where we work, and FIDL. There is the documentation as well that is automatically updated. I cannot stress enough, this is actually a cool thing. And we just want to let you go with this thought that the compilation, we think it is the future. And you see, I was watching like a Star Trek Discovery, and I was like, is this actually hex race? It is hex race. So, in 200 years, 400 years, apparently the compilation is going to be still a thing, as well as, unfortunately, the Win32 API. So with that, time for questions.